So now we look at what is called the Wigner transformation. Some of you may already have learned this in quantum mechanics, but it's a very brief review that we do. The idea is that one can assign a classical operator, or let's not call it classical operator, let's call it classical observable, OCL RP, corresponding to a quantum mechanical operator O hat RP, right? And the prescription to do that is OCL R comma P is integral R minus R by 2 O hat R plus R by 2 e to the power plus e to the power I P dot R d cube R, right? The inverse of this is the quantization prescription by Wheel. And here the idea is that for every classical observable OCL R comma P, the matrix representation of O hat R comma P, which is, we will say that the matrix representation of this, since we are saying the matrix representation, this becomes R prime O hat R of this quantum mechanical operator O hat is given by, so this is in the coordinate representation. So in the coordinate representation, is given by R prime O hat R is 1 over H cube integral OCL R plus R prime by 2 comma P e to the power I by H cube P dot R prime minus R dp. Note the measure is different. So this is identical to d cube P, where now P is a scalar matrix, and if you want to write down this, we can write down this as a vector R. But essentially the idea is same, right? Let's see if we can first really validate this for a case of a single particle. So let's take O hat as identical to the density matrix in the canonical ensemble, and there we have R prime rho hat R was 1 by V e to the power minus pi R prime minus R whole square divided by lambda t square. So following the Wigner transformation, we write this as R minus 2 rho hat R plus R by 2, and this becomes 1 by V e to the power minus pi R minus R by 2 minus capital R minus R by 2 whole square over lambda t square, which is 1 by V e to the power minus pi R square over lambda t square. Therefore, the classical observable, which is R comma P, is the Wigner transformation tells me that corresponding to this quantum mechanical operator, there is a classical observable which we'll call rho of capital R comma P, and that prescription is given by this. So we take it as integral d of r 1 by v e to the power minus pi r square over lambda t square e to the power I p dot r. This clearly is a Gaussian. There has to be a h bar over here. So did I miss an h bar over here? There is a h bar over here. Now this clearly is a Gaussian integral. Then this expression over here I can manipulate in the following way: r square minus I p dot r lambda t square over pi is identical to r minus I p dot lambda t square times 2 pi whole square, so that this gives me r square minus I p dot r lambda t square over pi plus I lambda t square over 2 pi whole square p square, which is now a scalar because p square is p dot p, so we will write this as p, but I clearly have this factor over here. So this is r square minus I p dot r lambda t square over pi minus lambda t square over 2 pi whole square p square. But I realize that there is a minus sign which is outside, so then the term that I need to add is plus. So this minus and this minus makes it a minus. Therefore I need to add a term which is plus lambda t square over 2 pi whole square times p square. If I add these two, then you see this particular term is identical to this, and therefore the exponential is pi over lambda t square r minus I p lambda t square over 2 pi whole square plus lambda t square over 2 pi whole square times p square, which is going to be e to the power minus pi over lambda t square r minus I lambda t square over 2 pi times p whole square minus pi over lambda t square, and I have lambda t 4 raised to the power 4 pi square p square. So this gives me lambda t square and then I have a pi over here, so that I have e to the power minus pi over lambda t square r minus I lambda t square over 2 pi times p whole square e to the power minus lambda t square over 4 pi times p square. Therefore rho of r comma p is 1 by v, and then I have d of r e to the power minus pi lambda t square r minus I lambda t square over 2 pi times p square e to the power minus lambda t square over 4 pi times p square. However, note that I have made a severe mistake in the sense that I did not include a h bar over here. So if I have to include a h bar over here, that means this becomes h bar, right? This becomes 2 pi is replaced by 2 pi h bar. You have a h bar, you have a h bar, and here you have h bar square. Again you have h bar square, h bar square. So now, therefore, I have 1 over v lambda t square over 4 pi h bar square times p square. I have dr e to the power minus pi over lambda t square r minus r0 whole square, and this is clearly a Gaussian integral, and remember this has a measure of r square, so therefore you come up with the result that this is going to be 1 by v e to the power minus lambda t square over 4 pi h bar square p square, and this is square root pi over lambda t whole square raised to the power 3. My mistake, sorry, this has to be pi times lambda t square raised to the power 3, which is equal to 1 by v. You have lambda t whole cube e to the power minus lambda t square over 4 pi h bar square p square. Good. So this becomes, you see, the thermal volume times e to the power minus lambda t square over 4 pi h bar square p square. Now let's focus on this term. So now lambda t is beta h bar over 2m pi raised to the power half. So that lambda t square is going to be beta, sorry, this has to be h square over twice m pi. So let's rewrite this now therefore as beta h square over twice m pi times 1 over 4 pi h bar square, which we will write down as 1 over 4 pi square h bar square, and h square I note is that 2 pi times, not 2 pi but 4 pi square times h bar square. Therefore this is beta over twice m 4 pi square h bar square divided by 4 pi square h bar square, so that this is beta over 2m. So essentially what you have is r, this row of rp, the classical observable corresponding to the phase space to the quantum mechanical operator rho hat, gives you the classical observable, which is lambda t over v, that follows from this relation e to the power minus beta p square over 2m, and this is exactly the canonical phase space density that we derived when we did classical statistical mechanics. So now let's apply the reverse. So we want to use the quantization principle, and essentially that says that if I have a classical operator Rp, I can get the corresponding matrix element of the quantum mechanical operator in the coordinate representation as 1 by h cube dp o cl r comma p. This is r plus r prime by 2 p e to the power I p dot r prime minus r over h bar. And in our case, I know that OCL corresponds to rho, the phase space density, which goes as lambda t over v e to the power minus beta p square over t 2m. So that essentially I have O hat r as 1 over h cube dp e to the power minus beta p square over twice m e to the power I p dot r prime minus r over h bar. Good. It's the same trick. So this is a vector integral. So it's the same trick now. We take these two and write this as beta over twice m p square minus twice I m beta h bar r minus r prime minus r p dot, right, which becomes minus beta over twice m. I have p, vector p minus im over beta h bar r prime minus r whole square, and then I have minus im beta h bar whole square r prime minus r whole square, so that this becomes very nicely p minus p0 whole square, and then I have a minus minus makes it a plus, but then I have I square which makes it a minus. I have m square over beta h bar square r prime minus r whole square times beta over twice m, so that this becomes beta over 2m p minus p0 whole square minus this beta gets cancelled, it gives me 1 power of beta, because this is beta square over here. I get m over here, and then I get 2 beta h bar square r prime minus r whole square, so that the matrix elements in the coordinate representation of this operator rho becomes 1 by h cube. There is something which we have missed. We have missed this factor which will come in over here, which is going to be lambda t over v. So I have lambda t over v, and then I have integral over dp e to the power minus beta over twice m p minus p naught whole square e to the power minus m over 2 beta h bar square r prime minus r whole square, right? This is a standard Gaussian integral which we have been doing so much, so that I can immediately write down this as 1 over h cube square root pi. So this is going to be square root twice m pi over beta raised to the power 3, and then I'll have e to the power m over 2 beta h bar square r prime minus r whole square. Now recall that the thermal de Broglie wavelength lambda t was beta h over twice m pi half, right? And if you look at this expression, then this is going to be m 2 beta times h square 4 pi square. So which we write down as pi. This gives me 2 m pi beta h square. So this is the mistake I made in the earlier expression, and you immediately see that this is going to be pi over lambda t whole square. And this together is going to give you the inverse of the thermal volume, and you recover the result pi square over lambda t square r prime minus r whole square. So that you have the result which we derived when we looked at the ideal gas, that in the coordinate representation, that the density matrix look like this. So therefore we have now a very nice way of going from the classical to the corresponding quantum mechanical representation. So given a classical operator, we can go to the quantum mechanical operator, or given a quantum mechanical operator, we can go to the classical operator.